On November 6th, astronomers expected the third ever interstellar visitor to look like a comet. Instead, fresh images from the Virtual Telescope project revealed something compact. No shimmering tail, but a silent anomaly racing past Earth. Yet the numbers say it's moving as if shedding 5.5 billion tons of material we just can't find. What force is driving 3I Atlas, and what are scientists missing? The search for answers starts now. Gianluca Masi and the Virtual Telescope project faced the dawn sky with a sense of anticipation. On November 5th and 6th, 2025, their Celestron C14 telescope, perched in the hills of central Italy, tracked a faint target just above the horizon. The moon, still bright and low, scattered light across the field, making every exposure a challenge. Yet frame after frame, the object appeared not as a sweeping luminous comet, but as a compact point, steady, silent, and stubbornly unremarkable. The images, released to the public within hours, defied expectations. Instead of a billowing tail or a wide, glowing coma, 3I Atlas showed only a tight, unresolved glow. Even after careful stacking and calibration, the processed photographs revealed little more than a star-like dot, with only the faintest hint of a surrounding haze. For a comet racing toward the sun, this was an anomaly. Masi's team worked through the complications of twilight and moonlight, using robotic mounts and long exposures to pull every possible photon from the background. The object's path matched predictions, confirming its interstellar origin, but the lack of visible gas or dust left astronomers puzzled. The equipment had performed as designed, the data had been double-checked, and yet the classic signs of cometary activity were missing. The path was confirmed, the behavior was not. For scientists and skywatchers alike, the question was immediate. Where was the gas, the dust, the drama? The Virtual Telescope images set a new baseline, a record of what 3I Atlas truly looked like as it swept past Earth, and the beginning of a deeper mystery that would soon challenge the very models used to explain comets from beyond our solar system. Inside NASA's Jet Propulsion Laboratory, analysts sifted through the latest tracking data, searching for patterns that gravity alone could explain. But the numbers refused to cooperate. The predicted path for 3I Atlas, based on Newtonian mechanics and the known pull of the sun and planets, diverged from reality by a measurable amount. Night after night, the object's position crept away from the model, never wildly off course, but enough to register as a persistent, quantitative puzzle. The deviation was not random error. Over several weeks, the accumulated difference reached nearly 4 arc-seconds, a gap that dwarfs typical astrometric uncertainties for a well-tracked comet. To match the observed trajectory, JPL's orbital solutions required the addition of a force, something nudging 3I Atlas gently but steadily as it hurtled through the inner solar system. In most comets, such non-gravitational acceleration is the signature of outgassing. Sunlight heats the nucleus, volatile ices vaporize, and jets of gas erupt, pushing the comet ever so slightly off its gravitational track. For 3I Atlas, the best-fit solution implied an acceleration near 0.02 millimeters per second squared. On paper, this subtle push seemed unremarkable, but when translated into the physics of mass loss, the numbers ballooned into a challenge. To produce the needed thrust, a comet of this size would have to shed material at a staggering rate, on the order of billions of tons over just a few months. Avi Loeb, known for his outspoken views on interstellar mysteries, calculated that the required mass loss approached 5.5 billion tons. Yet the images from the Virtual Telescope project and independent photometry showed nothing close to that level of activity. No vast tail, no dramatic dispersal of dust or gas. The math did not add up. The discrepancy sharpened the mystery, turning a visual curiosity into a concrete physical dilemma. For the JPL team and outside theorists alike, the only way forward was more data, more images, more spectra, more nights spent chasing a faint, stubborn visitor across the sky. Only 3 times in recorded history have astronomers confirmed an object entering our solar system from the vastness between the stars. The first, discovered in 2017, was 1I Oumuamua, a name now synonymous with cosmic mystery. Oumuamua shot through at an angle and speed that ruled out any solar system origin. It displayed no visible coma or tail, yet drifted slightly off its predicted path, a puzzle that sparked years of debate. Some argued for exotic explanations, while others searched for hidden, mundane causes. Just 2 years later, in 2019, 2E Borisov arrived. Unlike its predecessor, Borisov behaved as a classic comet. Jets of gas erupted as it neared the sun, and telescopes tracked a growing halo of dust. Its chemistry and activity mirrored the comets that have circled the sun for billions of years, offering a reassuring point of comparison. For the first time, astronomers could study interstellar ice and dust up close, using the same tools and models developed for homegrown comets. Now, with the arrival of 3I Atlas in 2025, the catalog of interstellar visitors grows by one more. Each detection stands as a rare astronomical event, separated by years and made possible only by new, wide-field ski surveys and better computational filters. The diversity among these three objects is striking. Where Oumuamua was dry and enigmatic, Borisov was active and familiar. 3I Atlas appears to straddle both worlds, showing signs of cometary activity, but also presenting unexpected behavior. This growing sample hints at a much broader range of materials and histories among the debris ejected from distant planetary systems. For astronomers, every new interstellar object is a chance to test old theories and glimpse the hidden processes shaping worlds beyond our sun. Spectrographs trained on 3I Atlas returned a sparse chemical fingerprint. Instead of the strong water vapor lines that define most comets, only faint traces appeared, levels so low that some teams questioned if the classic ice-driven activity was even present. Meanwhile, polarimetry readings raised further questions. Light scattered from the coma showed polarization angles and intensities that diverged sharply from those seen in solar system comets, hinting at unusual dust structure or composition. Brightness curves refused to cooperate with standard models. On multiple nights, the comet's apparent magnitude surged by a full half point, then faded again, with no clear pattern or solar trigger. Some observers speculated about outbursts or fragmenting jets, but the images showed no dramatic change in shape or size. Instead, a subtle brightening seemed to radiate toward the sun, suggesting a jet or fan directed sunward, an orientation rarely seen and difficult to reconcile with the observed lack of dust. China's Tianwen-1 orbiter, circling Mars, caught a different picture. Its instruments detected a sprawling coma, stretching thousands of kilometers, in stark contrast to the compact glow seen from Earth. This discrepancy between instruments and perspectives left researchers debating whether the coma was evolving rapidly or if each vantage point revealed a different facet of the object's behavior. With every new data set, the puzzle deepened. No single instrument could tell the whole story. The conflicting results pushed the scientific community toward coordinated multi-wavelength campaigns, hoping that only by comparing every angle and every spectrum would the true nature of 3I Atlas come into focus. Within days of the virtual telescope images going public, the conversation around 3I Atlas split in two directions. On one side, scientific teams worked methodically, cross-checking data and debating possible explanations through peer-reviewed preprints and closed-door meetings. On the other, viral headlines and social media feeds erupted with wild speculation, claims of alien probes, secret technologies, and cosmic conspiracies. The rush for answers fueled a surge of preprints, with researchers eager to publish first, sometimes before data had been fully vetted. Behind the scenes, competition for observation time on the James Webb Space Telescope grew fierce, with international teams lobbying for precious hours and accusing rivals of holding back results. Meanwhile, established astronomers urged caution, reminding the public that extraordinary claims demand extraordinary evidence. The scientific community pressed for open data sharing and transparent analysis, hoping to keep the debate grounded in observation rather than hype. As the next observation window approached, the gap between careful science and sensational hype widened, setting the stage for a public reckoning over what could and could not be known about this visitor from the stars. December 19th, 2025 stands as the next critical milestone. On that date, 3I Atlas will reach its closest approach to Earth, about 270 million kilometers away. Around the world, observatories large and small are preparing for a coordinated observation campaign. Imaging teams have already scheduled precise imaging runs, radio tracking, and spectroscopic sweeps, aiming to capture every possible detail as the object passes through its most accessible window. The logistics are immense. Time on major telescopes is booked down to the minute, while amateur astronomers coordinate online to fill in coverage gaps. For many, this is a rare opportunity to witness an interstellar traveler in real time, and to collect data that could answer questions raised by the first images. The outcome is binary. Either new observations will reveal the mechanisms behind 3I Atlas's puzzling activity, or the mystery will deepen, driving further debate. The countdown is underway, and the global scientific community is poised for what could be a defining moment in the study of objects from beyond our solar system. Interstellar objects like 3I Atlas appear only once every few years. Yet, each arrival rewrites the boundaries of our knowledge. Right now, astronomers worldwide are racing to interpret the data. In a universe of unanswered questions, every new image is a reminder. Discovery never waits for certainty.